Okay. Well, we'll go ahead and get started. People might trickle in as we go because I'm not particularly stringent about what time people show up, so whatever. Let's go ahead and talk about class logistics. Many of your faces are familiar to me, but not all of them. So I feel like we should go through all the things to make sure everyone's on the same page about how things work. It's pretty straightforward. Really, the only two things you actually have to know as far as like if you're actually enrolled in this class, to pass the class, you need to fill out the attendance form and do the weekly reflections. That's really it as far as passing the class. We'll talk more about like the structure and things, but really, of all the things I might say, if you are enrolled in the class, meaning you registered with a CRN, then you need to do those things. If you just got added via the Google form or you sent me an email and I added you, then I would still love it if you did those things, but they're not required of you. Everyone should have gotten an email from me either saying you're enrolled in the class and you need to do the things, or you're not enrolled in the class and you don't have to do the things. So hopefully you all got an email from me laying out what you need to do. You're always welcome to ask. But let's go ahead and look at Canvas real quick so that everyone kind of see what's going on. And remind me of your name, please. Solara? Cool. I know there's a lot of names I feel like I should remember because they were in the co-class last quarter, but sometimes your memory isn't always that great. Okay, so let's go ahead and take a look at Canvas for a minute. And we will start with the syllabus, even though it's probably not the most important thing, but it's good to go over it real quickly just because so there's information in the syllabus part. We'll kind of skim through it here. You're welcome to attend class via Zoom if that's better for you, or if the weather's terrible, or if you're not feeling well. Those are all great reasons to attend via Zoom, or you just want to. That is also an option. You could be attending via Zoom right now if you cared to. That said, I certainly like seeing people in person. It is my preference that you come in person because I feel like I'm better in person than I am online, but do what you want to do. Also, if you have questions, ask them. I am happy to answer questions. I don't always think of all the things that I might not be thinking of. So if you ask questions, we go, yeah, that's a good point. Let's see. As far as getting a hold of me, email is best. That is the most frequent way or the most easy way that I will respond. There are other ways. You could call my office. I don't know why anyone would ever call my office, to be honest. But if you needed to, if something was really urgent and you need to get a hold of me, which doesn't sound like it would ever happen, but if that was the case, you could call, and if I was there, I would certainly answer my phone. My office is in Dutton Hall, right across the quad. You're welcome to come find me there. Also, my office hours are at these times in these places. Monday, Wednesday, 10 to noon in the library. Starting next week is when drop-in starts in the library. And then this week and the rest of the weeks, Monday, Wednesday from 2 to 3:30 and Tuesday, Thursday from 9 to 10:20 in C class or El Centro, which is just up by the MU. And then Tuesdays and Thursdays from 2:40 to 4 in CADS, which is over in the South Side. And that is this week. So if you're looking for help this week, I'll be there. I was there this morning. No one showed up. That's fine. I had things to do. So, but that's, if you show up, I'll definitely be there. As far as the class is a pass, no pass class. If you're registered for it, if you're not registered for it, you don't need to worry about the grade that you see in Canvas. Most of you will be seeing like a 0% grade in Canvas, or after you fill out the attendance form today, like a 5% grade for attendance. That's fine. Also, but even if you are enrolled, I just want to point out the attendance. I did do something slightly different this quarter. I went ahead and marked everybody absent for all the classes you haven't attended yet. And so then when you do attend them and you fill out the attendance form, I'll mark you present. So you will build up your attendance grade. It won't start off showing like 100% and then change whatever. It'll show off, start off showing 0%. And then after today, 5%. And then after the next class, 10%. Every class is like, right, there's 20 classes. Each class is literally 5% of your attendance grade. So every time you attend, your attendance grade should increase by 5%. And just so you all know how that works, you fill out the form, then I go look at the Google sheet that all the data goes to, and I go fill it in Canvas so you can see what your attendance grade looks like. I wish there was an easier way to do it, but that's unfortunately the easiest way that I have found to do it. So it's not hard to fill out. Well, in fact, we'll look at it in just a second here. In fact, let's look at it right now. So before I do this, actually, why don't you all do me the favor of scanning this QR code if you're able. Hopefully you're able to. See if I make it larger and do that. You want to do it, Rachel? Okay, yo, good job. All right. Okay, hopefully everyone, if you got it, I can also pass. Sometimes it's hard to scan the one up there. I'm also happy to pass one around if anyone needs to grab it. Anyway, so take a look at the attendance form. I'll go to it as well, so we can all talk about how I would love for you to do it every time. Also, I would recommend bookmarking the page as opposed to, you can just set it down, so I'll grab it later. As opposed to having to scan this QR code every time. Yeah, that's fine. I would bookmark it so you can just go to it whenever you need to. As far as that's not the right thing, James. Oh my gosh. Now I can't even get there. You guys are like, I've already done it. But just so everybody, there's one thing I want to point out that I would hope everybody will do right. So you put your email in there, right? Mine is jjparmenter@ucdavis.edu. Whatever, I spelled it wrong. Student ID number, you have to enter your 9-digit number. If you could enter the wrong number, but please enter the right number, because later on we actually do go input the data into our student, like, okay, what is this? I have some system basically for tracking how many students we serve, and I do need your correct student ID number to put input there, because that's actually what we input. So please do write your correct student ID number. Your first and last name written as literally your first name first, your last name second. No commas, no other things. Come on in. We're talking about how to fill out the attendance form for class, which you can totally, if you want to scan that QR code, that'd be great. You'll click on Co-16B because that's the class you're attending, how you attended. We were all attending live in person. And then importantly, the date you're attending class for. So if you watch the video recording later because you weren't able to make it to class, you should fill out the attendance form after you've done so. So even if I was watching, this class's video a week from now, I would still input today's date, which is 01, 09, and importantly, the entire year 2024. Sometimes people will just write the year 24, and then that comes up as like 0024. And then when I'm sorting the data by date, there's people that are way at the top. I'm like, why are they whipped? Oh, because they put 0024. So please put the whole 4-digit year, because it needs to be there. There was something else. Oh, as far as entering the attendance data, the one thing I do require, because I've had some issues with people in the past, unfortunately, is if you're making up a missed class, please do so and fill out the attendance form within 2 weeks of the missed class. So if you missed today's class and you want to make it up, that's great. Please do so before, today's the 9th, not the 8th, sorry. Please do so before 9 plus 14 is what, 23? Do it before the 23rd, and so on and so on. It's not that onerous, I think, and I kind of would hope people were keeping up with the class. But that's pretty much it as far as the attendance form. It's not that big a deal. Just do it whenever you come to class. Again, even if you aren't actually registered for the class, I would still really appreciate it if you did it, because we do track the number of students we serve over the quarter, and it does have play some small part in how much funding we get from a certain part of the campus. So the better our data looks, the better it is for our department, which is then helps us have more money to hire more people to serve more students. So it's all for you, really. Let's go back to Canvas over here. Let's see, what else I feel like that's weirdly in the way. Let's put that over there. Let's see, the attendance form. If you're absent, you can make up your absence. You can find the class videos either in Canvas, which I'll show you in a minute, or you can find them on YouTube. It's pretty easy. And there's a link to the YouTube channel, because I do have a lot of videos from previous times I've taught this class. If you want to go look at old videos of me going over some Co-16B topic, you're certainly welcome to. Yeah. About the class, if there's something impacting your success in math, please don't hesitate to talk with me about it. Or if I'm somehow negatively impacting your success with math, which I don't anticipate, but you never know. I try to be very welcoming to everybody and helpful to everybody. But if you're having a problem with me or one of your other teachers, there are some places you can go report that and get help with that. They're linked there. I've never really explored them, to be perfectly honest. As far as class, we meet 10:30 to 11:50 Tuesdays and Thursdays right here where you are. I'm going to show you examples. I'm going to make you do problems. I definitely encourage you to come prepared to write things down with a pen and paper, pencil and paper, iPad and tablet, whatever, however you like to write things down. Come prepared to write things down and do math. Accommodations. If I can do anything to improve your ability to succeed in the class, let me know. Last quarter, I think, I don't know, it was one of the classes last quarter, someone asked me if I could use a thicker pen. So I did, right? And it definitely, I think it really helped everybody see better what I was writing. My writing is mediocre at best. So if you aren't sure of something that's written on the screen, just ask. I'm happy to clarify. I try my best to write nicely, but you know, my penmanship is what it is. And then if you have formal accommodations through the Student Disability Center, some of you or some people have already let me know what they are. That's great. They usually don't really amount to being much in this class because there's no exams, there's no homework, right? I mean, you're certainly welcome to record me, but I'm already recording everything. So whatever you need, I'm happy to accommodate it, but I don't think there's much you all will need from this class as far as accommodations go. Zoom, everybody knows how to use Zoom. You're welcome to attend via Zoom if you want to. I encourage you to attend via Zoom if you're not feeling well, or if the weather is trash, because there will be some weeks this quarter, because it's winter quarter and it's going to rain a lot, or hopefully it rains a lot. I mean, we need the rain still. So yeah, the class. So every quarter I try to encourage students to use the discussion tab in Canvas, which is over here, where you could like ask a question and I could write an answer, or one of your fellow classmates could write something. The nice thing about that is that it's really easy for me to type nicely in math type. I can write things like limits and stuff that actually look nice and not terrible. It's really easy to use LaTeX in this thing here, which is a way of writing that. So if you have questions you'd like me to answer, which yes, everybody will see your question, but they might also have that question. So if you're looking for help and you have not gotten help on Discord, although I will say join your class Discord as well. That's a useful place to get help as well. But if you want help from me, this is a great place to ask it. Your classmates might also chime in. Maybe someone will actually do it. I think one person last year, I was like, yeah, one person. Okay. But if you don't, it's not the end of the world. Nothing's the end of the world, right? It's just a math class. Back to the syllabus. I think we're almost done with the syllabus. Let's see, Zoom, some notes. Yeah, discussion. There's the usual kind of each unit in this course is connected to the previous things and so on and so on and so on. Mostly this quarter, we're going to be talking about anti-differentiation or integration. But before we get there, we will be talking about exponential functions and logarithmic functions and how to find their derivatives. But after we get through those two last types of functions, after that, it's really just integrals, anti-derivatives, that kind of deal. So kind of undoing the process of differentiation, which is why I'll remind everybody, it's really important to be pretty clear on the derivative rules from 16A, specifically how to take the derivatives of the trig functions, or how to take the derivative using the power rule, or what other functions. I guess that's really kind of it, right? Those are the only functions we really learned in 16A how to differentiate were x to a power or the trig functions, right? There's no really other special kinds of functions other than just combining them in all sorts of terrible ways and using the product rule or the quotient rule or the chain rule, which we'll talk about. Successful students spend 10 to 20 hours a week doing their homework. Let me ask. So for Tav's class, homework is not due, right? Just like last quarter. What about for Lee's class? Same? Homework? Is Lee's class? Who is in Lee's class? Just you, Evan? Okay. It's all right. Well, you're not the only one in our whole co-class. You're just the only one who happens to be here today. Do you know in Lee's class, is he assigning homework?
It's optional.
It's optional. Yeah, I would agree. Homework is highly recommended. So you really should do the homework. I can't say enough how much you should do the homework. You should all do the homework, do the homework, do the homework. Let me say it one more time, do the homework. Did I mention you should do the homework? Doing the homework is really important. So, I mean, the only way you're going to learn math is by doing math. I can't say it any more blatantly. You have to do the homework. Well, that's not true. You don't have to do the homework. But if you want to do well in the class, you have to do the homework. It is optional. Let me ask. Tab is just assigning problems from the book. Do you know, is Lee assigning problems from the book as well? I think he is.
If I remember correctly, it's problems from the book.
Yeah.
From what I saw, you pretty much teach directly.
Yeah. Neither of them have added me to their Canvas yet, which is mildly annoying since I emailed them a while ago, but it's fine. I'm sure they'll both add me at some point.
Looking at the thing you posted, it's technical problems 1, 2, 3,
cool.
4, 5.
Yeah, right on. So I will offer to all of you, if you will do the homework, you are welcome to turn it into me and I will grade it if you would like feedback on it. You're not required to do this. You don't have to do it at all, but I will gladly grade your homework if you want some feedback. But you have to do it. And you need to do it regularly so that you're ready for, I think Lee has quizzes. I'm not sure. Yeah, so definitely. I can't say it enough. I'm going to keep saying it. I'm going to say it so many times. It's going to get, but do the homework. Please do the homework so that you are prepared for the quizzes, for the tests, so that you're not scramble before an exam to feel ready for the exam. If you get in the habit of just doing it when you have the time to do it, now, everyone has all the free time. I know you don't have all the free time in the world, but make time to do your math homework so that you don't feel like it's all piling up before a quiz or an exam. But really, if you want to turn your homework on Tuesday or Thursday in person, like I would prefer a physical copy because it's easier for me to grade a physical copy. I suppose you could also email it to me. That might be, I could probably figure out how to grade that, without too much difficulty. But really, like I am more than happy to grade a homework assignment or multiple homework assignments for all of you every week if you do them. And I think as a student, I certainly would have loved to have gotten the feedback. So
I was wondering, generally speaking, what would the response time be on it? Because for Lee, we get it Tuesday night and it's due Thursday, but on Wednesdays I'm pretty much in class.
Sure. Good question. That is a fair question. I could certainly see finding, I have a relatively good amount of time on Fridays, so I could see getting it done before the next week. I would probably say what I could actually do, the easy thing is once I have it done, I could actually scan it and email it back to you so you could have it as soon as possible.
Yeah.
And then also you would be welcome to grab the physical copy whenever, but for speed, I could do that. It's hard to say exactly what it'd be because I don't know. Because no one's really ever taken me. I offer every quarter. I'm like, your homework's not due. Great. I will grade it. I think one person one time turned an assignment to me. Let's be the quarter where that's different. Let's have everybody do it. It'd be great. I would love it. I'd be thrilled. It would be more work. I'm not going to lie. It does take some time to grade your homework assignments. I'm happy to do it if you do your homework. All right. What else here? Office hours, see above. You can also get help from student tutors, from other math specialists. I should point out, if you look at our webpage, the AATC webpage, let's minimize this just a little bit here so I can go over there. If you go to the math part of it, excuse me, and you scroll down, way down past the classes, you can see when the other math specialists have office hours as well. Clara is all virtual, but she can help with lots of things. Grant, you can see that he's in El Centro Monday, Wednesday, Friday, 9 to 11. My office hours are on there. You can find Jen in lots of places at lots of times. You can find Sarah in a couple places at a couple times. All of these people can help you with Math 16B. And also, if you take stats at some point, Sarah, myself, and Jen too can help you with stats as well. So if stats is in your future, we're there for that as well. What else? Oh my gosh, that's always in the way. Okay. You're not there. Okay, back to the syllabus. And I think that covers the syllabus. So before we go over to the modules, any questions about the syllabus? Okay. If you have questions later, totally fine. So the syllabus is what it is. It's there for you to look at and be like, oh yeah, there's this thing. But really, if you're going to Canvas for this class, you're really going to look at the modules because the modules is where everything actually is. All the things. Oh gosh, that's not what I wanted to do at all. What? Oh my god, that's. I clicked on a PDF back here and accidentally brought it to the web page. I'm smooth. So I was trying to get. Oh my gosh. Okay, there we go. Finally. Okay, great. Let's move you out of the way. So later on this course, so you're seeing my view, which are things you can't see as a student. Anything that's not like checkmark green over here, you wouldn't actually be able to see on your Canvas page. It doesn't matter. Later on, this will be live, like the last 2 weeks of the quarter. I would ask that everybody fill out the course evaluation because that's how my supervisor sees feedback about me. Some useful links. This just shows when and where my office hours are. Here's another link to the class attendance form. You should all bookmark it. A link to the class Zoom if you want to attend via Zoom. Here is a link to my playlist on YouTube. I think it's sorted by the most recent videos first. You can sort it however you want. Here's some other short videos I made that are not on YouTube. They're on like we were making a page. I think we don't really add videos to this anymore, but there are some old videos there that are worth checking out if you're looking for more content. Here's the link to where the class notes will be. So whatever I write over here that you see, you can't see my hand over here that I'm trying to be like, you can see it. Well, eventually you like, when you see what I'm doing over here, I'll be writing stuff over here and I'll upload those notes to Google Drive and then I'll link them from Canvas. Grant's website is always a great place to get more information. Oh my gosh, except why am I not smart enough to open it in one click? No, good question. But if you look over here real quickly, Grant 16B class, there's lots of notes about various topics that we will be covering. Yeah, all the stuff. Grant is great. He's one of my coworkers. Let's see, what else? We have, oh, interesting. Why do I have that twice? Oh, I know this is a different place. These are some short videos I made for 16B way back when. Like 5-6 minutes long, just covering various topics. Then we also have some other video lessons that myself and others. So there's lots of video. You can go watch videos for days if you're looking for, and they're labeled by topic. So if you're looking for some more instruction on a certain thing, I would encourage you to look in this spot and in this spot here to see if there's something that might be like, oh yeah, there he's talking about trig integrals or whatever I'm looking for. Also Professor Kuba, well, he was a professor here. He was one of my, actually I had him as a teacher way back when. His website has lots of homework problems, lots of solutions, practice exams, stuff like that. So if you're looking, there's lots of resources to go look at. And then my website is not a great resource, but it does show what my office hours are and what class I'm teaching. And there's a picture of my cat. So, and then here's where I'll be putting the class recordings and written notes. I'll probably put other stuff down here like practice tests and stuff like that. I just hadn't added those modules yet because we don't need them yet. All right. I think that's everything. Questions about anything? Solara, Natalie, Evan, Jamie, Rachel, Peyton, and what's your name? Martin. Cool. I might remember them on Thursday. Let's see. Yes.
All of the reflection due dates are like 2 days off. Does that matter?
When you say 2 days off, what do you mean? It's a good question.
Yesterday, like reflection 1 was late.
Yeah. And I made the first one due super early. It's still available until the 12th. So yeah, all the reflection due dates are like they become available on like a Thursday and they're due like on a Saturday, because I would prefer you do them like right at the end of the week so that you can kind of sum up what you did that week. And then going to the next week and be like, oh, the student said this and they're asking about this. Cool. That said, they're open for an entire week, but you are correct in that they do close. And once they're closed, that's kind of it. So if you're doing the reflections because you're registered for the class and you need the reflections, you have a week-long window to do them, but then they do go away. So please do them within that week. And also just to point out, so to pass the class, you have to get a 75%. The attendance is worth 70% of your grade. The reflections are worth 30% of your grade. So you at least have to do a couple of the reflections to pass the class. You could get like 100% on your attendance, which would be 70%. And if you did 2 of the reflections, they're each worth like 3%. So that'd be 6%. So that would get you to 76. But you should probably do more of them just because you might miss a day of class. It could happen. But yeah, passing the class is not hard. If you do the things, just do the things. Also, the reflections are super easy, by the way. Like they're not, and there's not any sort of math in them. It's just me asking you like, what'd you do in class this week? What do you want me to talk about next week? Do you have a joke for me? What's the best book you read? Like I asked some sort of not mathy question about like what you've done interestingly. Have you eaten and you were nice? I don't know. Trying to come up with new ones, but it's always hard to come up with good questions. So I think I came up with a few new ones this quarter. We'll see if I remember what they are. But yeah. Yes. Other questions? Well, if questions come up, you're always welcome to ask them. And typically, if you ask me something that I think everyone should know the answer to, like if you ask me via email, I might post an announcement on Canvas saying like, somebody asked me this and I think you all should know about it. And then I'll say like, here's the thing. Yeah. All right, I guess we should talk about math. That's what we're here for. See if I can find the thing. Cool. Yes. Such a glare. That's what I don't like about this laminated is it really glares. All right. You can see that okay? Yeah, looks okay. All right, I think I have some notes somewhere about what I'm doing today. Not that I particularly need them, but sure. Let's talk about exponential functions. I feel like I'm very in the way here. Let me move this picture. Sorry, it's killing me. That's better. Over there. Exponential functions. Move this up a bit. Okay. What to say about exponential functions? Well, let's start off with some examples. So probably my favorite exponential function to talk about is the function f of x equal to 2 to the x. And that's kind of your standard exponential function. You have some base, 2 in this case, raised to the x power. And the fact that you have a constant number to the x is what makes it exponential, right? That variable is in your exponent versus g of x equal to x cubed. This is not exponential, right? This is a polynomial. I guess technically it's a monomial since it's only one term, but it's still a polynomial. So for an exponential function like this, it's really kind of nice to have a good idea of what these functions look like. And so I'm going to start by graphing this one. Normally, I would graph it just by drawing the usual kind of shape, but let's be a little bit more precise when we graph this one just to kind of really feel it. So I'm going to plot some points. X and then 2 to the x. So I'm going to pick some easy values for x and then find the corresponding y values. So I might start off with like x equal to 1. 2 to the 1 is 2. And x equal to 2. 2 squared is 4. And x equal to 3. And 2 cubed is going to be 8. Now that's probably as big as I want to go because otherwise my graph is going to get kind of off the chart. And then we can go the other direction. Well, in fact, let's go to 0. Ooh. What's 2 to the 0? Right. Cool with that? All right. And then 2 to the negative 1 is 1/2. 2 to the negative 2 is 1 over 2 squared, which is 1/4. And 2 to the negative 3 is 1 over 2 cubed, which is 1/8. So those are the points we're going to plot. I should also mention, before we plot these, you have a very useful tool at your fingertips all the time. It's a great graphing tool, Desmos. I highly recommend if you haven't played with it, getting familiar with it. Someone showed me a super cool thing the other day that I didn't know about. If you graph like, I don't know, some function x squared plus 2x minus 3, and you want to know what this derivative looks like, you can just type its derivative in there. I thought that was the neatest. I was like, what? You can just, now it doesn't tell you what the derivative is. We should know the derivative is 2x plus 2. Oh, look, it's the same line. Neat. Anyway, I thought that was just, I was blown away. I was like, that's so cool. I was really kind of like, that is easy. But you can also use this to graph things that you're not familiar with. So like, if I wanted to know what the graph of 2 to the x looked like without actually having graphed it, I could type 2 to the x, like, oh, it's going to look like that. And if you zoom out, you can see it gets steep really fast. The thing I kind of think about when I think about exponential functions is eventually they grow faster than any polynomial function. Eventually, now it's kind of hard to see here because things are so steep, but eventually this 2 to the x will catch up to that x cubed and cross it if you go up. But it's so hard to see because like they're so vertical anyway. But eventually exponential functions do overcome any polynomial function, which I think is a neat fact. But if I was going to graph this by hand, trying to make it kind of look as nice as possible, I plot some points over here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, and then I would do my best. So 2 to the 0 is 1. So I get the point 0, 1. I get the point 1, comma 2. I get the point 2, comma 4. I get the point 3, comma 8. I got 0, 1 already. I got negative 1, 1/2, negative 2, 1/4, negative 3, 1/8, and then I try and graph it the best I can. But really, the point is that kind of every exponential function looks like this. It kind of goes up to the left, up from left to right there's no other way to describe it other than in this exponential shape. That is literally the name of this shape, that's the exponential shape. That's what an exponential function looks like. It's increasing really, really fast. But if I wanted to say graph another one, I wouldn't spend the time finding all these points. For example, if I was going to graph, say, y equal to 5 to the x, well, I would kind of just say, well, I know I'm going to have the point 0, 1, because that's always going to be one of the points if we haven't shifted it some way up or down or left or right. And then it's going to have kind of the usual shape. Now, if I graphed both of them together, yeah, the 5 to the x1 should be a bit steeper than the 2 to the x1. That's kind of it. A few things to know about exponential functions. Well, some properties. The first property I would kind of note is that the domain is all real numbers. You're going to get everything from negative infinity to infinity. There isn't an x value you can't plug in, because again, when I think about domain, I know it's been a while. When I think about domain, the only kind of functions that have restricted domains are functions where there's potentially division by 0, or where there's a square root or an even root. Oh, I should make this big, sorry. Or where there's a logarithm. I don't see any of those three things here, so that typically means we have an unrestricted domain of the entire real number line. I should point out, small point to the side here. There are a few other functions that have restricted domains. They're inverse trig functions. I don't think we really talk about those in this class, so I'm not going to worry about them. But if your teacher says something about them, we can certainly talk about them. But they usually don't get covered in the 16 series, so I wouldn't worry about it. Yeah, I know. The range, on the other hand, is limited. We don't get any negative values as our outputs. We don't even get 0 actually. So the range here is everything from 0 exclusive to infinity. Or all positive real numbers. A few other things, we definitely have a y-intercept, which is going to be 0, 1. We have no x-intercept because, again, we're not hitting the x-axis. I feel like there's one other thing I usually like to talk about. Oh, yeah, I know what it is. And well, we'll say that. So I will point out that this function, actually, I will ask you, is this function an increasing function or a decreasing function? If we go from left to right, are we getting bigger or getting smaller? Bigger, so we're an increasing function. So this function is increasing. But I'll point out, it's only going to be increasing if the base is larger than 1. So it's increasing as long as the base is greater than 1. I really feel like there was one other thing I wanted to say. Oh, I know what it was. There are two other things I want to say. Exponential functions are continuous, right? There's no breaks in the function. When I graph it, I don't have to lift my pencil off the paper. And also, the function is differentiable everywhere. In fact, I should clarify. When someone says, or when I say a function is continuous, or when I say a function is differentiable, it is implied that I mean everywhere. This function is continuous everywhere. This function is differentiable everywhere. If it was not, I would say it was discontinuous or not differentiable, even though that usually means it's like not continuous at 1 or 2 points. It's kind of weird. Let's look at another example just to kind of see one other thing that can happen. Yeah. So let's look at the graph of sugar. I keep my notes in order here. Also, if I move things off the page, off the visible screen too fast, let me know. I'm happy to like be like, oh yeah, I can go back. So if there's something you need to see that that you've missed, don't hesitate to say, James, I want to see that. Let's graph one more. Let's graph g of x equal to 1/3 to the x. So when we were graphing 2 to the x, as the powers got larger, the outputs got larger, right? 2 to the third was 8. 2 to the fourth is 16. 2 to the fifth is 32, right? 2 raised to a higher and higher power gets bigger and bigger because you're just multiplying by 2 again and again and again. But when we take this number that's less than 1 and raise it to a higher power, the output's going to get smaller. Because 1/3 times 1/3 times 1/3, every time you multiply by 1/3, the number actually gets smaller, not larger. In fact, we could make a little table if we really wanted to. I don't really want to, but it will. If x is 1, 1/3 to the 1 is just 1/3. If x is 2, 1/3 squared is 1/3 times 1/3, which is 1 times 1 over 3 times 3, which is 1/9, which is smaller. And if x was 3, 1/3 cubed would be 1/3 times 1/3 times 1/3, which is 1/27. So as the x values get larger here, the y values are getting smaller and smaller. And then on the flip side, if the x values go in the negative direction, if x is -1, when I think about negative powers, I think about reciprocals. So 1/3 to the -1 is the same as the reciprocal 3 to the +1. Whoops, which is 3. 1/3 to the -2 is the same as 3 to the +2, which is 9, and so on and so on. So really what this actually ends up looking like is the normal in quotes exponential graph, but flipped across the y-axis. So instead of increasing from left to right, it's actually going to be decreasing from left to right. Oh, I know what the other thing I wanted to say on the previous. I'll come back to the previous page and just say, because there's one more thing I needed to write on the previous page. I finally remembered what it was. You guys might already know. So here's what this graph is going to look like. It is decreasing from left to right. Still has the same domain, still has the same range, still has the same y-intercept, still has the same lack of x-intercepts, still continuous, still differentiable, but the only difference here is this function, g of x equal to 1/3 to the x, is decreasing. And that's going to happen whenever your base is between 0 and 1. I say between 0 and 1, not just less than 1, because all of our bases actually have to be positive. It's decreasing when the base is between 0 and 1. Oh, the thing on the previous page that I forgot to say that is important, the other feature or property that this graph has, in fact, all these graphs have, is that there's a horizontal asymptote. So this graph has a horizontal asymptote at y equals 0. Now, unlike rational functions that we saw last quarter, where the horizontal asymptote was to both sides, for exponential functions, it's a one-sided horizontal asymptote. You only either get it on the right or on the left. So here, it's a horizontal asymptote to the left. Here, it's a horizontal asymptote to the right. It doesn't really matter as far as like how you write it. Like you would still say the horizontal asymptote is y equals 0. But the reason I mentioned this is because there's one. So sorry, I know I hate when I go back to a page and let me write a couple more things. There's 2 more things I want to write here. Graphically, we can see these. If I asked you for this function here, what's the limit as x approaches negative infinity of this function? Well, as we go way, way, way out to the left, the y values are getting closer and closer and closer to what number? Yeah. So just by graphical analysis, we can see that as x goes to negative infinity, the limit of the function 5 to the x is 0. On the other side, if we look at the limit as x goes to positive infinity of the same exponential function 5 to the x, we can see that as we go way, way to the right, the function is going to get really, 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 really big. So the limit is going to be infinity. And that's pretty typical for exponential functions. One side will go to 0, the other side will go to infinity. If you haven't like flipped it around or shifted it, but essentially that's kind of the idea. Over here, just to kind of continue with this theme, over here we're going to get the opposite things being true. Here, the limit as x approaches negative infinity of 1/3 to the x is going to equal infinity, because as you go to the left, the function gets really, really big. And the limit as x goes to infinity of 1/3 to the x is going to be 0. Because as we go to the right, we can see that that's going to get closer and closer and closer and closer to 0. I should also point out, you don't have to have the graphs to be able to figure out what these limits are. It's nice. I like having the graphs, but they're not required. Let me show you what I mean. If I wanted to find the limit as x goes to infinity of 1/3 to the x. Well, let me point out, you can do a couple things here. The first thing is you can write this as the limit as x goes to infinity of 1 to the x over 3 to the x. And here's a trick that math people use all the time. What's 1 squared? What's 1 cubed? What's 1 to the 75th power? What's 1 to any power? Right? Even if it's a negative power, even if it's a fractional power, 1 to any power is 1. So 1 to the x, no matter what x is always going to be 1. So I can rewrite this as the limit as x goes to infinity of 1 over 3 to the x. And now here's where we ask ourselves a couple questions. As x gets really, really, really big, 3 to the x also gets really, really big. Right? 3 to the 1,000th power is gigantic. 3 to the even larger number is even bigger. And then 1 divided by a really big number, is it really big or is it really small? So we get closer and closer to 0. That's how I justify what's happening here. I'm like, oh yeah, I'm getting 1 over a really big number, so it's going to be a really small number. On the other side, if we look at the limit as x goes to negative infinity of 1/3 to the x, I might start by doing the same thing. I might start by saying, well, I've got the limit as x goes to negative infinity of 1 over 3 to the x. Skipping that middle step there. I don't like being raised to a negative infinity power. My brain just doesn't work for my brain. I know, I'm like, I've got 3 to the negative infinity. I should know what that is, but I don't. So I'm going to rewrite it so that my power, I always get to think of as being positive. You don't have to do it this way, but it works for me. So I'm going to rewrite this as the limit as x goes to negative infinity still. But now I'm going to bring this 3 to the x up to the numerator. But when I bring it up to the numerator, I have to change the sign of the exponent. I'm going to rewrite this as 3 to the negative x instead of 1 over 3 to the x. Still the same thing, but just written in a different way. Why have I done this? Well, I've done this because now, in my mind, I get to see this as being a positive exponent because I've got 3 to the negative infinity. But negative is positive. So I really have 3 to the infinity, and that's a really big number, right? 3 times 3 times 3 times 3 times 3, an infinite number of times is going to be infinitely large. So to me, if I can, I like to try and look at these limits by making my exponent be positive. And you almost always can do this kind of trick. So I like it that way. these limits do come up on occasion, which is what I typically try not to just talk about things I like to talk about for the sake of it. Usually, occasionally I might go off on a tangent about anchor days or something, but here we actually do use this, right? This is an important fact when you're graphing these things, when you're trying to, when we're looking at improper integrals later, this kind of piece of information is actually going to come up. So yeah. What else to say about exponential functions? What did you say in class yesterday? Like, that's not a good question, James. Not at all. Like, tell me everything you said in class. No, like, how far did you talk about like, and so I'm specifically referring to Tavern here. Did you talk about shifting things up and down or left and right? Okay. Reflecting them as well. Oh, okay. Well, I want to talk about reflecting them because I will just point out this actually is literally the same as the graph of 3 to the negative x, which is really just the reflection of the graph 3 to the x in the y-axis, right? If you take your function and you change the sign of x to negative x, it reflects it in the y-axis. So 3 to the negative x is the reflection of, in fact, let me write this down here. Yeah. So here's what y equal to 3 to the x looks like. Again, taking liberties with how well drawn this is. And y equals 3 to the negative x. You're literally taking the same graph and reflecting it in the y-axis. Kind of cool. So that's how people often say, oh, I don't really see this like this. I see this like this. They're really the same. Let's do some transformations, I guess. I'm assuming we did not talk about logarithms at all in class. Okay, those are coming up for sure. But let's talk about some transformations. We have lots of time. Take it slow down for a minute. You're kicking through the wire. I think about what else I need to say about exponential functions. Yeah, sure. So sometimes we move things around. We might want to say, for example, graph y equal to 2 to the x minus 4. So this is our usual exponential function shape, but we've shifted it. Which way have we shifted it? Up or down? Left or right? It's definitely down. On the other hand, just to kind of, I just want to point out, this is going to shift down by 4. I will point out that if we had instead graphed y equal to 2 to the x minus 4, that would be a shift of 4 to the right. I know it's always tricky. The horizontal ones always are kind of feel backwards, but I'll clarify that in a minute is why it's right. But it does always feel like if we're subtracting, it should be left, but really it's not. It's really to the right. Yeah, but I think I have a good way of thinking about it. So I'll talk about that in a minute. But here, if I'm shifting down 4, what I'm really going to think about when I'm graphing, always with the smearing of the pen. I'm going to think about what happens to the horizontal asymptote. My horizontal asymptote would have been y equals 0. But now I'm literally going to move it down 4 to y equals negative 4. So 1, 2, 3, 4. Here's my new horizontal asymptote. Notice how I'm not really plotting any points at all. Is it laziness? Partly, but it's also because we don't really care a whole lot about all the points. We want to get the general shape. We definitely want to include whatever intercepts we have and also whatever features we have. Speaking of intercepts, I could either find the y-intercept by setting x equal to 0, not too terrible, or my y-intercept, if x equals 0, y is going to equal 2 to the 0 minus 4, which is going to be 1 minus 4, which is negative 3. I could also have just thought about the fact that my previous y-intercept was 1, and if I move it down by 4, 1 minus 4 is negative 3. And then I would draw it. I know I'm going to have an x-intercept here. That's not always the case. If I draw it, I'm going to get something like, Do make sure when you draw these, they shouldn't be pointing straight up. Exponential functions do not have a vertical asymptote. They just sometimes look like it because they're so steep, but they never, ever, 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 ever have a vertical asymptote. They always, always, always have a horizontal asymptote. But I do see that I have an x-intercept here, so I should find the x-intercept. So if I set y equal to 0, so y equals 0, I have 0 equal to 2 to the x minus 4, or 4 equal to 2 to the x. Here, that's pretty easy to solve. I know that if x is 2, 2 squared is equal to 4, so that's going to be my x-intercept. Sometimes these can be a little bit harder to figure out. So my x-intercept there is the point 2, 0. Okay. So let me give myself more room for this other one here. Just to point out kind of how this one works. So let's talk about y equal to 2 to the x minus 4 versus y equal to 2 to the x. And why I have to shift a 4 to the right and not 4 to the left. Here's what I like to think about. What would x need to be to get the same y values I would have gotten before? So let me show you what I mean. If I was graphing y equal to 2 to the x, I know you don't need to make this table again. I'm going to make it again for illustrative purposes, but if you don't want to write it again, you don't need to. So before, when I was making this table, I had x values like 0, 1, 2, and 3, and corresponding y values that were 2 to the 0, 2 to the first, 2 to the second, and 2 to the third. I also had negative x values, -1, -2, -3, and the corresponding y values of 1/2, 1/4, and 1/8. So what I'm going to do over here is I'm going to ask, what would x need to be to get the same y values? Well, in fact, let's do it like this. I would love to have 2 to the 0th again. So I want x minus 4 to be 0. So that 2 to the 0th is still 1. But if x minus 4 needs to be 0, well, I can do some quick math here. If x minus 4 equals 0, x needs to be positive 4. And if I want x minus 4 to be 1, then x had to be 5. If I want x minus 4 to be 2, then x had to be 4 more than that, which was 6. So every x value has to be 4 larger, so that when I subtract 4 from it, I get back to the same x value I wanted to get the corresponding y value. So this entire graph is going to be this graph, but shifted 4 to the right, because every x value has to be 4 larger than it was to get the corresponding y value that I wanted. Here I have x is 0, y is 1. Here I have x is 4, y is 1. X is 1, y is 2, x is 5, y is 2, and so on and so on and so on. So I always think about it in the context of, oh, how much more or how much less does x have to be to get the same y values I had before? So now I have x being 4 and y being 1. It's kind of terrible to graph. And x being 5 and y being 2. And x being 6 and y being 4. And x being 7 and y being 8. And that's how values to the left, right? X could be, if x was 3, then 3 minus 4 is -1, and 2 to the -1 is 1/2. So it just continues on in the usual way: 1/2, 1/4, 1/8. Like, it's hard to draw so small. That's kind of how it looks. I guess I should label my y-intercept. It's usually good practice to do so. So the y-intercept here, if x is equal to 0, then y is going to be 2 to the 0 minus 4, which is 2 to the -4th, which is 1 over 2 to the 4th. And 2 times 2 times 2 times 2 is 16. So it's 1 over 16, which is very small. Although not that small in the world of small things. I still have a horizontal asymptote of y equals 0. So it didn't shift up or down, I shifted left or right. When you shift right or left, you don't change the horizontal asymptote. I still don't have an x-intercept because I didn't shift down, so I don't end up crossing the x-axis. All right, so what else to say about exponential functions? Good question, James. It always feels like we're trying to say all these things, but also like trying to get to the real meat of things. And I'll be honest, the real meat of things, we got time. Is going to be talking about the derivatives of these functions. That's where we're really going. It's not the only thing, but it's definitely something I think that I would like to show you right now, because I think it's definitely where you're going to go eventually. So here's a fun, interesting fact. If f of x is equal to e to the x, wait. I can't just throw e to the x and even talk about its derivative before we talk about it. Let's talk about e to the x. First of all, what is e? It's a number. It's also a letter, but like in math, it's a number. And it's approximately how much? 2.7. 2.718, whatever. Nobody cares. It's 2.7. That's what you need to know. Okay, we have time. Yeah, we have time. We should talk about where this number comes from. Where does this number come from? It's a good question. Well, yeah, we'll do this. So we're gonna kind of do an experiment. No, it's not an experiment. We're gonna do some stuff. You probably don't need to write this next part down. You're always welcome to write down whatever you want, but this part is going to be kind of gross for a second. So how many of you have heard of like compound interest? Right? It's like you put money in the bank, you get interest, and then you get interest on your interest. And there's a formula for it. So compound interest, and I think you actually do talk about, let's see. Is it in this section here? It might be in this section. I feel like you talk about compound interest maybe in section 4.2. Maybe it's only in the context of this example I'm about to give you though. So here's how compound interest works. You have some principal, some amount you're investing or charging, giving a loan as. It's called P, that's your principal. And then you're going to multiply it by 1 plus R over N to the NT power, where N is the number of times you're compounding. And it shows up twice. T is the number of years you're doing it for. R is the interest rate as a decimal. So if your interest rate was like 15%, it would be 0.15. And P is your principal, your initial investment, whatever. And then this is equal to the amount of money after T years. So for example, if we invested $2,000 earning 10% interest, interest maybe, compounded semi-annually, how much money would be in our account after 1 year, 2 years, 5 years? Let's talk about the 1 year example, because that's actually when we can calculate by hand and kind of see what's happening. So normally, if I said you invest $2,000 and you earn 10% interest, after 1 year, you'd be like, well, I get 10% back. So 10% of 2,000 is $200. So at the end of the year, you'd have $2,200. So if we were not compounding, then the amount of money after 1 year would just be your $2,000 times 1 plus the interest rate, which was 0.10. And 2,000 times 1.1 is going to be 2,200. Right? You had your investment of $2,000, you earned 10% interest on it, you got back $200 plus what you invested. On the other hand, if we are compounding semi-annually, meaning twice per year, and I picked that because it's easy for me to calculate, to be perfectly frank, here's what happens. In the first half of the year, you earn half of the interest. So in the first 6 months, you're gonna earn 5% interest on your $2,000. So you're gonna take your $2,000 and you're gonna multiply it by 1.05. The 1 to keep the $2,000 you had, the 0.5 for the 5% interest. So that's gonna end up being $2,000, and 5% of 2,000 is $100, right? Because 10% of 2,000 of 10% of 2,200, 5%. So that's gonna be $2,100. That's how, so after 6 months, I pay you half your interest. And then for the next 6 months, I'm going to pay you interest on that $2,100. So for the next 6 months, you're going to take that 2,100 and multiply that by 1.05 to get 2,100 plus whatever 5% of 2,100 is, which is $105. You got more money by compounding your interest. And that's what happens when you compound your interest. And now it's not like there's a word I'm looking for. I always searching for words I can't find. It's not something you can do forever, right? You can't like keep doing this and get just infinite money. There is a limit, literally a mathematical limit to how much you can get doing this kind of thing. And that's where the number E comes into play. So we don't really need to answer the rest of these questions. The point is just that you can kind of see the difference between not compounding and compounding. Really what I did here, what I should have done here is just written it as 2,000 times 1 plus 0.10 divided by 2 to the 2 times 1 power. That's exactly what we did. We took our 2,000, we multiplied it by 1.05 and 1.05 again, or in other words, we multiplied it by 1.05 squared, which is exactly what we did. Okay, so now here's the real deal. Here's where we're going to see where this is probably, how much time do we have? This is probably not the most important thing you'll ever see, but it is neat, it is interesting, and it is something it's nice to know about. And it will come up in class. Even if you don't actually have to know how to do this, it's still good to be aware of what's happening. So let's say, it's all my favorite part. Let's say I lend you $1. Or you lend me $1, either way. Someone lends someone $1. So we're going to lend $1. We're going to charge 100% interest because we're not that nice. And we're going to loan you the money for 1 year. We want to know how much money are we going to get back at the end of the year based on how many times we compound the interest per year. So let's take a look at the formula. How much money do we get back at the end of 1 year? Well, I'll remind you of the formula for compound interest. The formula is that the amount of money after T years is the principal times 1 plus R over N to the NT power. Well, let's fill in what we know though. We know that the number of years is actually 1. So the amount of money is going to be, after 1 year, I'm not going to write that in there, is going to be the principal, which is $1 times 1 plus the interest rate, which is 100%, as a decimal is just 1, over N, which is the number of times we're compounding, which we are going to vary, raised to the N times T, but T is also 1, so it's really just raised to the N power. So the amount of money after 1 year is going to be 1 plus 1 over N to the N power. And let's make it a function of the number of times we're compounding it, because that's actually what we're going to change. All right. Of course, I don't have my numbers with me, so I'm going to make stuff up. So let's see what happens. Let's make a little table here. We've got N and we've got A of N equal to 1 plus 1 over N to the N. So let's say we compound it just once per year, right? Normal interest, we're not compounding it. If I plug that in, I get 1 plus 1 over 1 to the 1, which is 2, which makes sense, right? I lent you $1, I charge you 100% interest. At the end of the year, I get back the $1 I lent you plus the $1 of interest. Right on. Let's see what happens if we compound it semi-annually. We're going to get 1 plus 1/2 to the second power. Well, 1 plus 1/2 is 3/2. 3/2 squared is 9/4, which is 2.25. So just by compounding it twice per year, I earned an extra 25 cents. Yay me, I'm gonna be rich. What about quarterly? Well, then the math gets hard, and I don't think I brought a calculator. Did I bring a calculator? I never know if I brought a calculator. 1 plus 1/4 to the 4th power is 5/4 to the 4th, which is, okay, 625 divided by 256. I don't know what that is. Did I bring a real calculator? Not a terrible phone calculator. It's terrible. No, it didn't. Phone calculator is worse. Fine. So use my phone calculator. It's awful. Don't worry, we're about to get to the point. So that ends up being about 2.44. As this process goes on, the number gets larger and larger, but not without end. So let's just go, let's say we do it 12 times, 1 plus 1/12 to the 12th power. I guess I have to do some math here. I should have written this down, but I didn't because, yeah, I didn't. That's why, because I didn't. It's about 2.6. And if you compound the interest every day, daily, so you did 365 times, or 366 if it's a leap year, which it is this year. We have class on the leap day. That's going to be approximately, let's actually do it, James, fine. It don't have to be, I can do the math. Let's raise that to the 365 power. What do we get? We get about 2.714. And so here's what's actually happening. As the number of times you compound it gets larger and larger and larger, it goes to infinity. This quantity gets closer and closer to E. And that's the limit for compound interest. So literally, and this is something I imagine your teacher might say at some point, E is defined, not just approximately, E is defined to be the limit as n goes to infinity of 1 plus 1 over n to the n. There are other ways of writing it, but this is one of the ways of writing it. They might use x's instead of n's. They might rewrite it in a way that looks a little bit different, but this is it. That's actually the definition of the number E. Just like pi is defined to be the ratio of the circle's circumference to its diameter. E is defined to be this thing. Kind of weird, but kind of neat. Okay, so we had 10 before, right? Right, yeah. 11:50? Yes, okay. I'll try to go eat lunch, yeah. That's important to do. Okay, so that's E. We kind of took a big side trip over here. Now we're back to the real math. E is a great number. It's actually called the natural base for reasons that will become clear maybe Thursday, maybe next week. It's great. It's wonderful. But it's also just about 2.7. And definitely, of all the exponential functions you might graph, y equal to e to the x is the one we graph the most. It looks just like the rest of them. The only thing that is maybe remarkable about the graph is that unlike any of the other bases, the slope of the tangent line at the y-intercept on this graph happens to be 1. That is the only graphical thing that's, well, it's not the only graphical thing, but it is a graphical thing that's remarkable. So right there, that slope is equal to 1. And it's different for any other base. Now, really what I'm doing here, what I'm exploiting, is the fact that, well, I think we learned in 16A that another way to interpret the slope of the tangent line is as the what? The derivative. Slope of the tangent line is the derivative. The derivative is, I mean, it's not the only thing the derivative can be interpreted as, but one of the ways to interpret the derivative is as the slope of the tangent line. Okay, so here's the deal. Here's what's super cool about the function e to the x. At whatever point you pick on the graph, the y value, oh look, the y value there is also 1. the y value is also the value of the slope of the tangent line. Or in other words, for f of x equal to e to the x, the derivative is also e to the x. It's kind of almost annoying because it feels like you've done nothing. So let's look at a more interesting example. Let's look at a chain. So what I would say is whenever you learn a new derivative, the first thing you should do is try chain rule versions of it. So just like way back when, the derivative of sine of x is cosine of x. And then the derivative of, let's say, I don't know, let's say the derivative of sine of x squared minus 3x. All we've done is replace the argument with something a little bit more complicated. I know the derivative of sine of some stuff, or I should say, back it up. The derivative of sine of x is cosine of x. So the derivative of sine of some stuff is going to be cosine of that stuff. And then the chain rule says we have to multiply by what? The derivative of that stuff. That's why I say the word stuff. Whenever I say the word stuff, I'm always thinking, oh, I've got some stuff. It's not just x. I'm always going to have to multiply by the derivative of that stuff. So here, the derivative of sine of some stuff is going to be cosine of that same stuff. It doesn't change yet. And then we multiply on the outside by the derivative of that stuff, which is 2x minus 3. The reason I point this out is because in the very same way, if I wanted to find the derivative of, say, e to the x cubed plus 5x, well, we just learned that the derivative of e to the x is e to the x. I'm just taking the word x and replacing it with the word stuff, the word x, the letter x, and replacing it with the word stuff. So the derivative of e to the x is e to the x. The derivative of e to the stuff is going to be e to the stuff. But then what do I have to multiply by? Every time, the derivative of the stuff, which in this case is going to be 3x squared plus 5. We just learned a new rule. The rule for taking the derivative of exponential functions with the natural base. So let's write it down a little bit more formally, just for fun. And not just for fun, for keeps. So we have two rules. The easy rule, the derivative of e to the x is e to the x. And then the more general rule, there's like 3 different ways you could write this. I would prefer to write it using the words I actually say, but I'll write it 3 ways because there's the book way and there's another way. So I would write it as the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Now, I'm aware that's not a very mathy way of writing it. So 2 other ways of writing it. You could also write it as the derivative of e to the f of x is equal to e to the f of x times f prime of x. Or a more book way of writing it is probably to write it as the derivative of e to the u is equal to e to the u times du dx. But either way, it's the same deal every time. The derivative of e to the something is e to that same something times the derivative of that something. Or the derivative of e to the u is still e to the same u times the derivative of u. Every time. Cool. Nice. It's nice when things work the same every time as most of math does, but not all math. Sometimes math gets weird, but we're not there yet, so it's okay. What time is it? We got 4-ish minutes. So let's do a little bit of, why not? Let's add in all the rules. I know it's been a while since, it's been at least a couple weeks probably since you've really done some math. Let's say, what if I wanted to find the derivative of e to the 2x times cosine of x? What rule would I need to use here? I mean, there's a couple correct answers. There's not just one rule. What rules would I need to use here? It's one of them. You're allowed to just say words. You can say things. I know it's weird, right? What's one of the rules I might need to use here for taking derivatives? The chain rule, definitely, because I have an e to the stuff. What's the other rule, noting that I have e to the 2x multiplied by cosine of x? The product rule. Yeah, product rule. So I think my hearing is also not the best sometimes, so I think I heard what I wanted to hear, but didn't hear that, it's also fine. So product rule, I need, and you can, I'm just gonna write it. So it's gonna be the derivative of e to the 2x. Let's just write it like that. The derivative of the 2x, we'll deal with that in a minute. Times the not derivative of the other thing, just leave it alone. Plus, and then you switch. You leave the first thing alone. You multiply by the derivative of the second thing. I suppose I can use more parentheses there. You don't really need parentheses around the x there, but it's also not a bad idea. All right. The derivative of e to the stuff is e to the stuff times the derivative of that stuff. And the derivative of 2x is just 2 times the cosine that's still over there. Plus e to the 2x times the derivative of cosine is negative sine of x. And then I mean, if I was doing this on an exam, I would leave it as is. If I was told not to simplify. If I was going to simplify, I would rewrite it as 2 e to the 2x times cosine of x minus e to the 2x times sine of x. I would not factor out e to the 2x, even though you could. I would factor out e to the 2x if I was trying to maybe like set this equal to 0 and find critical points. But we're not doing that, so I wouldn't. Yeah, sure. So just, this is a good idea. As a quick reminder, because you all definitely, I know for sure, all of you 100% know your trig derivatives, but just to remind you of them anyway. Sorry, I'm terrible at handing things out. It's not my forte here. Just so that we all are on the same page, I would like everybody to be reminded of them. Let's just write them all down right now. So the derivative of sine of x is cosine of x. The derivative of cosine of x is sine of x. And the derivative of tangent of x is secant squared of x. Here's a nice pattern that I talked about last quarter, but I'll talk about it again. Listen to the words I'm saying. The derivative of tangent is secant squared of x. The derivative of what's up? Oh, thank you so much. I was making terrible mistakes. Good God. If I make a mistake, it will happen. Please don't hesitate to say something fast. Because everyone's like, wait, yeah. Say thank you for saying the words, Rachel. I appreciate it. So in fact, to go along with that, every cofunction, cosine, cosecant, and cotangent will have a negative derivative. And the pattern I want to mention is the derivative of tangent is secant squared. The derivative of cotangent is cosecant squared. I'm just putting a co in front of each of those. And then, of course, we need the negative sign because we know every cofunction has a negative derivative. So the derivative of cotangent of x is negative cosecant squared of x. In similar way, the derivative of secant of x is secant of x times tangent of x. And then we're going to take all three of those, the secant and the tangent, and turn them all into their corresponding cofunctions. So the derivative of secant is secant times tangent. The derivative of cosecant is cosecant times cotangent with a negative in front. The negative cosecant of x times cotangent of x. I don't think these are going to come up all the time, but I definitely do think they will come. They are useful in making up examples where you have to use the product or the quotient or the chain rule. So definitely make sure that these are committed to memory. They're going to come up. And I think that's a good place to end. All right. I will see you all on the next day of class, which is Thursday at 10:30. Feel free to attend however you want. Although I love seeing you in person, please come in person if that works for you. And there's something else. Oh, make sure you fill out the attendance form.